Yeah, hi, welcome everybody. We are representing Research IT here at Berkeley. Myself, Chris Patoric, and Clint Hamilton are domain consultants, and we will be giving today's training. So just wanted to make sure, can everybody see my screen okay? Okay, awesome. Great, all right, so we'll go ahead and get started. Sorry. Yeah, so just a couple of quick announcements that we wanted to blast really quickly. So we have the cloud computing meetup that happens every month. And so feel free to click on the link for more information on that. And then we also have platforms and services available for researchers working with sensitive data. So if you're interested on that, feel free to click on that link. And then we are also looking for domain consultants. So if you are interested in working potentially part-time, please feel free to reach out to us for that. Okay, so like I said, we will be giving today's training on the introduction to Savio. So just a couple of quick notes before we get started. I'm going to be presenting from slides that we have prepared, and these have been shared with you. And so you can access them through these links here. Some of the parts of this demonstration, of the training will be demonstrations. So if it'll be great for y'all to follow along, especially for some of the data transfer examples. But if it's too fast or you're still not quite understanding what's going on, these materials are available for you to view in your own time. And then, yeah, all the materials are posted here. So feel free to follow along if you want. Okay, so just a quick overview of what we'll be covering today. We'll be talking about some of the introductory concepts behind parallel computing for folks that aren't super familiar with high performance computing. And then we will talk about the general architecture and system capabilities for Savio. We'll cover logging in, data transfer. And so I will cover these first three parts. And then my colleague, Chris, will be covering submitting and monitoring jobs. And my colleague, Clint, will be covering using Python in Open on Demand on Savio. Okay, so we'll start off with some of the basics here. So in very simplistic terms, Savio is a collection of really powerful computers, and we call these computers nodes. Each node will give you access to a different number of cores or processors. So for example, our standard node, we have 24 cores. But if you're to kind of imagine this in your head, then you could kind of consider each node to be an individual computer. And then another part of Savio is a set of really big and really fast hard drives. And all these computers and hard drives are networked together, and that essentially makes up the bulk of Savio. And so having access to different nodes will give you the capability to do parallel computing. And so I'll talk really briefly about the two main types of parallel computing. There's shared memory. And so those of you who have used C or C++ before might be familiar with OpenMP, which is a really common shared memory tool. And the key aspect of shared computing is that all the computation is done on the same node. And this means that objects can be shared in RAM memory. So for example, if you have two processes running, then they can both write to the same data array. And the other type of parallel computing is distributed memory. So for distributed memory, you'll be working across multiple data nodes. And so you can kind of imagine that being like working on the same problem with two different devices. And a really common tool here is MPI, and this focuses on passing information between nodes. Okay, so now that you have a general understanding of what Savio is, we'll talk a little bit more about how to actually get access to Savio. So for most people, the most common way to get access to Savio is through a faculty computing allowance. And a faculty computing allowance is available to all Berkeley faculty for free, and you're allocated 300,000 service units. And so just to kind of explain that a little bit more, one service unit is equivalent to 1 core hour on one of our standard nodes. And a standard node has about 24 cores. So to use one node for 1 hour would cost 24 service units. And this might look slightly different depending on the type of node that you're using, as well as the number of nodes and the time. And in addition to that, if you need to purchase a node that you want to use regularly for your research group, we also offer those for purchase through the Condo Cluster program that is linked here. And then if you're an instructor and you want to use Savio for your class, we also have an instructional computing allowance that you have access to. And then we also have a really convenient portal called the MyBRC portal that you can use to request online access to your computing allowance. But just one thing to note, the requests are submitted online, but they still need to be reviewed manually. And this process can take about a week or so. So just keep in mind that once you submit your request, it'll take a little bit for it to be approved. And then lastly, if you are a graduate student or research staff and you want to get access to Savio, the best way would be to speak to your PI to get access through their faculty computing allowance. Okay, so getting more specifically into what Savio is, we'll talk about its system capabilities and hardware. So Savio has more than 600 nodes with more than 15,000 cores. It's a Linux cluster, and so it runs Linux in a command line interface, and it has close to 540 teraflops, which is just another way of saying that it can run a lot of computations very quickly. And it also gives you access to GPUs, so that's something that's available to you as well. And so about 40% of the computing nodes are provided by the institution for general access. So the university has essentially purchased those nodes and given them to a general pool for people to access through their faculty computing allowance. And then 60% of the computing nodes are contributed by researchers in the Condo program. So when people purchase those nodes to the Condo program and they aren't using them, then they are able to be used by FCA accounts. And so next we'll talk about the 3 different types of nodes on the cluster. So for those that might have worked with other high performance computing clusters at other institutions, the login node and the compute node will look pretty familiar, but the data transfer node might be slightly unfamiliar. And so we'll go over each type of node in more detail. So the first type of node is the login node. And basically when you log into Savio, you'll be on a login node. And so when you log in, and I'll go through an example of this in a bit, but you'll see something like LN001 or LN002, and that's telling you that you're on a login node. And so the login nodes are for non-intensive interactive work. So please don't log in and immediately start doing computationally intensive work. These nodes are generally for submitting and monitoring jobs, basic compilations, so like if you need to compile C or C++ code, and then managing the space, so like copying, deleting, and moving files. So yeah, now we'll talk a little bit more about the data transfer nodes. And like I said before, like these might be slightly unfamiliar for those that have worked on other clusters. But yeah, Savio has data transfer nodes that are used specifically for transferring data into and out of Savio. And so generally, or ideally, you would want to do all of your data transfer on data transfer nodes and not login nodes, for example. And so they have different web addresses. And so the login nodes will use this hpc.brc.berkeley.edu web address. And then the data transfer node will use the brc.berkeley.edu addresses. And then for certain applications, it'll look for an SFTP when you're trying to log in, but just remember that this won't work for hpc.brc. So just be aware that you might have to disable that feature. And then all of the nodes are connected to Savio's file system. So you don't have to work with your data specifically on a data transfer node. It's just for transferring data into and out of Savio. So like to your personal device or a stored drive or vice versa. And then lastly, we have compute nodes. And this is where all of your computation will occur. So for example, you might be using some nodes to run a parallel job using more than one CPU, or you might be doing a serial job on a single CPU. But do keep in mind, though, that whether you're using one core or multiple cores, for most of our partitions, the cost of using one node is the same. So basically, you can't use a partial node except for some of our more specific partitions, which I'll talk about in a minute. Yeah, and so there are different types of computing nodes. There are our standard cores, our Savio 2 nodes that have about 24 cores and 64 gigabytes of memory. And then there are other types of nodes. So for example, we have the Savio 2 GPU, which will give you access to use GPUs. And then another example is the Savio Big Man, which has more RAM storage. You can look at a more detailed list of all of our partitions as well as their specifications with the hardware configuration page linked here. But depending on the application, you might have to use different types of nodes. And the nodes are divided into different types of pools called partitions. So basically, each partition is a different category of computing nodes. And different partitions and different types of nodes will have different restrictions on what you can do. So for example, like most nodes are not going to allow you to use just one core, except for a few like Savio HCC, for example. And then there are different costs associated with using different nodes. So for example, using a Savio 2 node is going to cost more than using a Savio 1 node. And then any job that you submit has to be submitted to a partition that you have access to. And this is particularly relevant for condo users. So condo users, for example, can submit jobs to nodes that they don't own, but these jobs might be preempted, which means that they might be cut early if someone else with higher priority needs to use that node. And then, yeah, also some of the newer partitions are not available to all users. So just be aware of which partitions you have access to before you submit your job. Okay, and this is a conceptual diagram of Savio. Note that it is slightly outdated in that it doesn't show some of our newer partitions, but it's still good to just kind of show you the general architecture and framework of Savio. And so if you're the user, you'll log in through SSH or Globus or SCP, FTP, rsync, and rclone, which I'll talk a little bit about in a minute. And then you'll connect via the internet. And then when you do that, you'll end up in a login node, like I mentioned before. And then if you're transferring data, you will end up in a data transfer node. And then from here, you can see that we have all our computing nodes and the different partitions, as well as our file systems. And so one thing to note are the dashed lines here. So the black line here represents connections via Ethernet, which is relatively slow. And the red lines represent connections via InfiniBand, which is relatively fast. And so the home directory of your file system is only connected to the compute nodes via Ethernet, but the scratch directory is connected via InfiniBand. And I'll talk a little bit more about the differences in these directories in a little bit. But just remember that when you're running jobs, you want to make sure that you're submitting them from the scratch directory because the connection is significantly faster. So jumping off of that, now we'll talk a little bit more about the storage systems on Savio. There's basically three different places that you can store your data. The first one is the home directory, which will follow this general web address format, so the global home users and then your Savio username. And so the home directory is 10 gigabytes of backed up data. So if there's something that you don't want to lose, you'll want to store it in the home directory. But keep in mind, 10 gigabytes isn't very much. So yeah, just remember that that's a pretty limited option. There's the group directory, which might need to be requested in certain cases, but generally is 30 gigabytes for an FCA and 200 gigabytes for a condo user. And then last is the Scratch directory, which is the most commonly used for storage. And it follows this general address structure. So global Scratch users and then your Savio username. And like I said before, it's connected via InfiniBand. And so it's really fast when you're accessing data via a compute node. So this is really where you want to store all of the data that you would need to use during a computation. And all three are available to access from different types of nodes at any time. So like say, for example, like if you're doing a computation and you need to access something in your home directory, you can still do that. But just remember that it would be slow because that connection is slower. And then also if you need a larger amount of storage, we do offer extra condo storage for purchase. So just be aware of that as an option. So again, just to emphasize what I mentioned before, the Scratch, using Scratch is really fast, but the connection to the home directory is very slow. So if you're writing and reading a ton of files from your home directory, it can actually slow down access for other users. So please remember to primarily use your Scratch directory, not just for your benefit, but the benefit of other users. And so, yeah, Savio is certified for moderately sensitive data, which would be P2 and P3 by Berkeley standards. Savio by default is not sufficient for this type of storage, so you'll have to request a P2 or P3 specific project, which we can help you set up. And then if you have really sensitive data, so P4 data, we developed a new platform called SRDC. And so if you have really sensitive data, we'll still be able to help you with that, but we'll probably direct you to another platform that's not Savio. And so, yeah, if you're interested in learning more about SRDC or working with sensitive data, we've got the links to our documentation as well as more information on our website. Okay, so now that we've done the introductory stuff, we'll talk a little bit more about how to actually get onto Savio and how to get your data onto Savio. So to get onto Savio, you'll need to have a machine that gives you access to the SSH command. And this comes built in on Mac. It didn't used to come built in on Windows, but now you can access it through programs like PowerShell and Command Prompt. And if you want to use something with graphical interfaces, you're going to have to use an X server application like Mobile Xterm, which gives you access to that. And I'll talk a little bit more about that in just a second. You also need to set up Google Authenticator on your smartphone or device to generate one-time passwords. And I'll talk about logging in with passwords in a second. And then if you're following along in the slides, feel free to click on this link to get more directions on that. So to log in using the SSH command, you would open a terminal and then you would type in SSH and then your username at hpc.brc.berkeley.edu. And then once you type that in, it's going to prompt you for a password. And so you would start with your 4-digit PIN, and then you would type in your 6-digit code from the Google Authenticator. And so once you've logged in, then you can navigate around the directories using standard Unix commands like lscd, cp. And if you haven't used Linux or you're not familiar with other bash Unix commands, there's a basic tutorial that we've linked here. And so feel free to look at that. And so now I'll just go through a really quick example of how to log in using a command prompt. So just give me just a second to open that up. And is everybody able to see that?
Yes.
Awesome. Okay. Yeah. So for logging in, you would type SSH and then your username. So my username is CW87 at hpc.brc.berkeley.edu. And so you would type that in, and then it's going to prompt you for your password. So I would type in my PIN, and then I would get the code from Google Authenticator. And then once you type that in, you'll see that you end up in a login node. So I'm in LN003, like I mentioned before. So is everybody able to see those slides again?
Yes.
Great, awesome. So yeah, if you want to use a graphical interface, there are certain applications that will allow you to use that. But when you're logging in, you'll have to type in this -y when you're using the SSH command. And so to display graphical interfaces on your local machine, you'll need to use an X server application, like I mentioned before. So on Windows, there's Mobile Xterm, Xseed, Xming, and then on Mac, you have Xports. And so I will go into a more detailed example on how to use one of those in just a second. And then for editing files, we have a couple different options in Savio. So Savio has Emacs, Vim, and Nano built in, and you can use those tools to edit your files directly. And so, yeah, I will show you a quick example of what that looks like on Mobile Xterm. So just give me a quick second to pull that up. Okay. Is everybody able to see that?
Yep.
Awesome. Okay. So this is Mobile Xterm. It'll take you to this new window here, and then it'll prompt you for, and then we can use SSH to log in. So I'll type SSH whpc uc.berkeley.edu. And it'll prompt me for the password and the, yeah, so now I'm logged in again at the login node. And so if I wanted to use Emacs, for example, I would type in Emacs. I'll just give it a second to load. Yeah, I'm not sure if y'all can see that. That actually might be a different window. Sorry.
Yeah, we can't see it.
Yeah. How about now? Are y'all able to see that?
No, we can see it.
Yeah, so this is the Emacs graphical interface. And so, yeah, it's kind of a better interface for people that might not be as comfortable using Unix. So just be aware that you have that as an option. Okay. Okay, so now that we've talked about getting into Savio and how to move around, now we'll talk a little bit more about data transfer. So at some point, you'll probably have to transfer files from your scratch in your home directory to outside file systems. And so we'll cover 3 ways that you can do that on Savio. And so the first 2 ways will be used primarily for smaller data files, and then the last one will be for larger data files. So the most basic way to transfer files from command line is the scp command. And it looks a little like the SSH command, and you can use this in a Linux interface, so it's either Mac or Windows. And so what this looks like is that you'll type scp and then the location of your file. So we'll be using the Bay Area.csv file in this example. And then you'll type your username at DTN. So for the data transfer node, like I mentioned before, .brc.berkeley.edu. And then the little squiggly is a stand-in for my home directory. And so then you'll be prompted for a password. So you'll have to log in again to your Savio account. So I'll just do a quick example of how to do this. Yeah, so I'm in a login node, and so I will, actually, sorry. Yeah, just gonna open up sorry, just gonna open up another command prompt really quickly.
Looks like you're not sharing your screen anymore.
Yeah, sorry, I'm just pulling this up really quickly. Yeah, so say for example, I wanted to transfer the Bay Area.csv file. So I'm just going to navigate to where that file is at on my device. So if I wanted to use SCP, I would type SCP and then the name of the file, so the Bay Area.csv file, and then my username, dtn.brc.berkeley.edu. I want to transfer this to my Scratch directory. So I'll type that in, and then it'll prompt me for my password. So again, I'll type in my PIN followed by the Google Authenticator code. And then it'll give you this kind of little interface that shows you the progress of that. And so the Bay Area CSV is a relatively smaller file. So it's not going to take too long to transfer. But yeah, that is how you use SCP. So yeah, that's a really convenient option for transferring smaller files. So another option that you have is using SFTP. And so this is done through a multi-platform application like FileZilla. So after logging into most SFTP applications, you can see your file systems. And so I will transfer, we'll take another look back at the MobaXterm application, because this gives you access to the SFTP. And so going to go to
Christian, I'm just cognizant of time here, and I'm a little worried about.
Yeah. Okay. Yeah, for sure. We can skip this example actually, but yeah, just remember that for SFTP you'll need to use a multi-platform application like FileZilla, and then those other two, so SCP and SFTP, are primarily for transferring smaller files. If you want to transfer a larger file, you'll probably have to use Globus, which is our new tool for transferring larger files. And so this uses something called grid FTP, which is essentially just a really fast connection. And so I'm not going to go through an example here in the interest of time, but yeah, Globus is utilized primarily by setting up endpoints. And so essentially you would set up an endpoint on your personal device, and you could set up other endpoints like Savio, other computing clusters like NERSC and XSeed, B Drive, and then you can also transfer data to collaborators as well as other researchers not on Savio. And then, yeah, so the steps for setting up Globus are linked in this presentation, so you can go through that on your own time. But essentially, you would have to set up a desktop application called the Globus Connect Personal to set up your device as an endpoint. And then you would have to connect to Savio. So we've already set up Savio as an endpoint, and that endpoint's name is here. Yeah, and then you can use that to transfer larger data files. And so yeah, once you set it up, it's a really convenient application for larger data files. And if you're comfortable, you can also use a command line interface. And then we have, and then so for cloud storage options, the two most popular are Box and B Drive. And so just a few things to note here is that both of these services have kind of changed their storage guidelines a little bit. And so they're going to have, different storage quotas. So just be aware of those limitations. But anyways, so if you're transferring data via B Drive, then there's already a Globus endpoint set up for that. And so the links to set that up are in the documentation. And yeah, that's a really convenient way to transfer data between B Drive and Savio. But unfortunately, there is not an endpoint yet for Box. And so the only way to do that is by using rclone. And so rclone is a command line program that you can use to sync your files between Savio and Box V Drive. And so here are the instructions to configure that that you can go through on your own time. And then, yeah, once you set it up, it's pretty straightforward. So yeah, with that, I will go ahead and transfer it over to Chris. So.
Great, thank you, Christian. Okay, so let me make sure I'm sharing my screen here. Okay, so look, can folks see the slides? Okay, thanks, Amy. Okay, so I'm going to talk very briefly about software modules, and then I'll spend most of my time talking about submitting jobs to the scheduler that we use and some of the different partitions you can use and how you can think about submitting jobs that we'll use where your code will run in parallel. And then I'll hand it over to Clint to talk about some use cases with Python and using Open on Demand. So the first thing about in terms of software is that we have a lot of software available in Savio, but it's only available to you if you actually load it using a tool called environment modules. And so the basic way that you can do this is there are commands called module list and module avail, and then you can load these modules with module load. And when you do module load, then the software becomes available to you. And that's based on the back end that some environment variables are set in Linux to make that software available. So just to do a little bit of a demo of that, we can do, for example, module list. So I'm here on one of the login nodes. I can do module list. We can see there's not really much loaded right now, but if I do module avail, we'll be able to see all of the different software that we have installed on the system. So some of this has been installed by the system administrators, and that's the stuff sort of at the top here, some commonly used software and compilers, things like Julia, Python, GCC, the Intel compilers, and so on and so forth. A little bit further down, we also have software that's been installed by our consultants, and that's often installed at user request for particular more specialized software. So I could, for example, load, say, Python, one of the more recent versions of Python by doing module load, Python 3.9.12. So apparently I got the number wrong. So if I go back up here, it's 3.9.12. So what went wrong there? Oh, I forgot the module load command. So I can do module load Python 3.9.12. And then if I look to see what modules are loaded, I see that indeed that has now been loaded. And if I were to ask which Python I'm about to use, this shows me that indeed I'm accessing the 3.9 version of Python. One slight trick here is that some of the modules are available in a hierarchical or nested fashion. So if I tried to, for example, load OpenMPI, this is going to fail. And that's not because we don't have OpenMPI installed on the system, but rather because OpenMPI, the version of because OpenMPI is installed for particular versions of the compilers. So if instead I do module load GCC, then if I do module avail, what I'll see is that a particular version that OpenMPI is available, particularly for particular versions of GCC. And so I could now do module load OpenMPI at this point. And that will then work. And then module list will show that I have a somewhat older version of GCC and a version of OpenMPI that is compatible with that version of GCC. Okay, so now let's turn to thinking about submitting jobs. So Christian already mentioned that you can only run jobs on partitions that are available to you. So of course, the next question is, well, how do I know what partitions are available to me? So there's this command here where you can type in the name of any user, including yourself, to find out what partitions you have access to. And so if I just run that here on the login node, then what we'll see is these are all the different accounts and partitions that I have access to. So there are a bunch of these that I have access to because I have some sort of administrative privileges and various ways that I've used the system. But what you're more likely to see is something like this, that you might see either access to an FCA or access to a condo or both. So these initial lines here show that I have access to an FCA that is under my name. And then these later lines show that I have access to a condo, and this is actually a condo owned by the statistics department. So as Christian mentioned, well, I guess he didn't mention this explicitly, when you have access to a condo, you basically have regular priority, or you have high priority access to the particular kinds of nodes that your PI purchased. And so for the stat condo, we purchased some GPU nodes in Savio 2. And so we see this stat 2 GPU normal QoS indicating that I have high priority access to those. And we also purchased some Savio 2 nodes. And we see that based on this stat Savio 2 normal, that I have high priority access to those Savio 2 nodes. But for these various other partitions, for example, Savio 2 GPU, Savio 2 Big Mem, we didn't purchase any of those nodes. So I only have access to those nodes through the condo via Savio low priority. Now, in contrast, if we consider the FCA for essentially all of these different partitions, the partitions which are listed here, I have access to those under the Savio normal QoS, and that basically means I have sort of normal priority access to those nodes. So using this command will sort of give you a sense of under the different accounts that you might have access to, what are the different partitions that you would have access to, and at what priority level. Okay, let me talk a little bit about submitting a job. So this is the way that you would, I guess I should have mentioned it before, that basically the scheduler is the piece of software that manages the coordination of all the different jobs that you and your collaborators and everybody else on the system are running. And its job is basically to make sure that those jobs are started in a way that balances the use of the different users and in accommodation of the different priorities that different people have based on the type of account they're running under. So the basic way that you submit a non-interactive job, also called a batch job, is that you would write a small shell script, and it would look something like this. And in what looks like comments in the shell script, you would have these particular special comments, pound sbatch, that would provide the various flags or options that say how you want this job to run. So particularly important ones are you would specify the account. So this is under my FCA. You would specify the partition you want to use, and you would specify a time limit, the maximum amount of time that your job needs to run for. And then not in comments, you would specify the commands that you want to run. So a common thing to do would be to load one or more modules, and then to run one or more commands based on those modules. So let's switch back over, and we can see that I have, let's see, so see that I have a job script here, and that runs code in this calc.py file. And if I look at calc.py, that's just a Python file. It's just going to do a bunch of computationally intensive linear algebra that I won't bother to go into. And so at this point, I can submit this job using sbatch and then the name of the job script, which is job.sh. And we should see that it will return back that it's submitted this job. I can now do sq-j and the job number. And that will then tell me whether or not the job has started running or whether it's pending. And so we can see this job is currently pending. And that's what this state of PD means. So if I hit the up arrow and hit return, we can see if that has been able to start yet. Okay, so it's running now. Another thing we can do at this point is we can type wwall -j and then the name of the ID of the job. And this will give us a little bit of information about what's going on the nodes in terms of the actual computations. So it says it's using 3% of the CPU, and it's using about 3 gigabytes of memory out of the 95 gigabytes of memory that is available on the system. Another thing we can do is we can run srun with the job ID, and then, oops, that's not the job ID, and then --pty to get a terminal session, and then bash to start a shell. Okay, so it looks like that job already finished. So let's go ahead and resubmit the job. Okay, so that's still pending. So another thing I could do is I could cancel that if I didn't want it to actually run. I'm actually going to submit this using what's called a reservation, which you would not generally have access to. But in this case, we just set up a reservation to enable our jobs to run for this training so that they'll hopefully run right away. So now if I do sq-j with this new job ID, hopefully that will be running. Okay, so that's running. And if I now try to rerun that srun command to actually get a shell on the actual node where the job is running, so this is 199, what we should see is that I can get onto a shell on the node where the job is running. And usually it would not take quite this long. And so now if I type top, what I should see is I see the actual Python process running, and we see it's actually using well more than 100% of CPU. So it's using about either 3,000 or 1,000% of CPU. And that's because we have Python as well as some other software such as R set up to run linear algebra in parallel using a threaded basic linear algebra subroutine package. So that's why we're able to get sort of automatic parallelization of the linear algebra that was shown there. The other thing to notice is we are indeed on the compute node, and that's indicated because our prompt has changed and it no longer says LN002 or whatever it said before. It now indicates that we're on one of the compute nodes. So I can exit out of this with exit, and here I am back on the login node. Okay, so that was sort of a brief demonstration of running a job and being able to do some things to monitor that job, indicated here on the slide. I think we covered all of these already. I guess one thing that I didn't mention is that a very helpful thing to look at is, sorry, I lost track of my train of thought here. Oh, right, this is the last thing I wanted to mention is you can look post hoc after the job has run. You can run this saccount command and try and get a sense of, for example, if your job failed, why it might have failed and sort of what happened with the job. So I'm going to do that with this particular job ID. And this should show some indication of what happened with the job. It took about 34 seconds to run. The maximum memory use, which is what this max RSS was, looks like it's about 8 gigabytes, so 8,000 megabytes or 8 million kilobytes. So you can see some useful information about your jobs using that command. Okay, let me say a little bit about parallel job submission. So if you want to use multiple nodes in particular, you're going to need to carefully specify the hardware resources that you need. And that's basically done by, in addition to what we saw before, which was specifying the account, the partition, and the time limit, that there are some additional flags to Slurm that you can specify to say what resources you want to use in terms of the number of nodes and potentially the number of CPUs. So one thing I could do is I could say how many nodes I want to specify, either in the long form or the short form here. I could also say how many tasks I want to run per node. So that's basically how many individual processes I want to run to do my computation in parallel. And in particular, if I'm using threaded code, for example, like that threaded linear algebra that I mentioned, you can specify the number of CPUs per task. So by combining various combinations of these different flags of nodes and number of tasks and number of CPUs, I can set up my resources for various styles of parallelization. So one example is if I were running an MPI computation, then what I might do is just ask for a certain number of tasks and let the system figure out how many nodes it needs in order to satisfy the fact that I want to be able to run 40 MPI tasks in parallel. So this would basically allow me to run those 40 tasks. I could load the compiler, in this case, the Intel compiler and the OpenMPI that's set up for that compiler. And then I could run MPI run, and by default, MPI and Slurm are going to play nicely together. And so I don't actually need to specify how many tasks I want to use for my MPI job. I can just say MPI run, and it will automatically look up and see that, that I want to run 40 different MPI tasks at once. Once you've got one, in terms of actually understanding sort of what resources you have available within your code, you can make use of these environment variables that Slurm is going to set. And these will be available when your code is running. So you could have your code set up to do different things depending on the values of these environment variables. Okay, so some common sort of patterns that you might find that when you're setting up parallel code, you might want to use many CPUs on one node. So for example, to use OpenMP or threaded jobs, similar to what Christian mentioned. You might want to use Python or R or some other software to where you're doing the parallelization within the software. And that would be another case where you might want to use one node and many CPUs. Another case might be many nodes and many CPUs. So this could be like an MPI job that uses one CPU per task, or using Python or R or GNU Parallel to use many tasks, to run many tasks with one per CPU. Or you might have sort of a hybrid job, and this would be something where you might have many tasks, and each one of those tasks might themselves, say, be using multiple CPUs via threaded code. And so you can sort of manage all of this with those different flags that I showed on the previous slide. And we have a variety of examples of these in our documentation. Okay, next thing I want to mention is you can work interactively, and this is helpful for debugging or running sort of short jobs where you want to be able to sort of monitor and see what's going on while the job is actually running. So the command you would use to do this is srun, and then you need to specify similar flags to what we saw in the job script that we showed a few minutes ago. So this would be an example of how we would run an interactive job. I think for the sake of time, I won't actually demonstrate this, but if you run this, then what you'll see is there might be a delay while the system is trying to find resources for you to use. Hopefully it won't be too long. And then your job will start and you'll be put onto one of the compute nodes, and your prompt will change in the same fashion as it changed in the example I showed before when I logged into the compute node on which my batch job was running. So that would be the indication that you're then running on one of the compute nodes. And from there, you can load modules and run any software that you want, including running interactive GUIs of the nature that Christian mentioned before. And those, if you have X11 forwarding set up, those should then show on your display on your local laptop or desktop computer. Now, actually, we would generally recommend that you run graphical interfaces interactively using our Open On Demand interface, and Clint will talk about that and some of these things that you can do through Open On Demand in a few minutes. Let me mention a few of the other partitions and other ways that you can run jobs. One of the nice things about having access to a condo is that you can use nodes that in some sense don't belong to you. And that allows you to run jobs on a large number of nodes, and this is called bursting beyond your condo. The downside is that those jobs could be canceled if other users who have higher priority need access to those nodes. But this is a good way to get a lot of computing done basically for free. And if the system is not too busy, then you might be able to do this without your jobs being preempted. So just to give you a brief example of how this might work, I could, for example, say sinfo and then the name of a partition. So let me see how much activity there is on the Savio 3 node. That's what sinfo shows. So that shows that there are 152 allocated nodes, but there are actually 37 idle nodes right now that are available. So this would be a good time for me to try running, for example, a low priority job that needs to use many, many nodes. So for example, usually these would be batch jobs, but you could actually try this interactively. So here's an example of trying to use my condo, but running at low priority mode, so under the Savio low priority QoS, and requesting access to a large number of nodes, so say 20 nodes. So hopefully this would start, because I know from just having run that sinfo command that there are a large number of idle nodes. We'll see. So yeah, it tells me that it's waiting for resources. It might start up soon. It might be that the system is trying to collect resources for some other pending jobs in the Savio 3 partition, and it might not even though it looks like there are 37 that are idle, it might not actually give me access to those if it's trying to collect resources for some higher priority jobs. So I won't bother to wait any longer for that. I just hit Control-C to exit out of that. Okay, so the notion of HTC jobs, Christian mentioned this briefly. So some of our partitions, Savio 2 HTC, Savio 3 HTC, coming soon, Savio 4 HTC, allow you to request access to one or more cores on a node and only be charged for the number of cores that you request. So a standard way you would do this is you would say, I want to use one of those partitions. And then basically, often you would use CPUs per task as your flag to say how many cores you want to use. And in this case, you should only be charged for 2 cores instead of all of the cores on the node. And the Savio 2 HTC partition also allows you to run jobs for up to 10 days. So usually FCA jobs are limited to 3 days in runtime, and condo jobs, depending on how the condo is set up, may not have a runtime limit, or in some cases they might. But if you're using an FCA, then this Savio long QoS on this particular partition allows you to run some of those jobs. Okay, and then in addition to be able to run sort of serial code or code that just needs to run on a few cores, another way that you could do this is you could basically collect together a number of serial jobs into one sort of mega job or meta job. And you can do this either using a tool called GNU Parallel, or potentially using software like Python or R or MATLAB to basically run multiple computations or multiple tasks all within a single Python or R or MATLAB session. Okay, so I think I actually mentioned many of these commands already in terms of getting information about your running jobs and information about monitoring your jobs. One other one that is useful to mention is this check usage command, and this basically allows you to see how much usage there's been of your FCA. So for example, for this particular rail FCA, this says that out of the 300,000 service units that was made available, they've already used about 30,000 of those. So you can get some indication of how much resources you still have left to use. And then let me just see where I am. Okay, so then just briefly, I just want to mention one other tool that we have available for monitoring jobs. We've set up, one of our interns a couple of years ago set up a very nice tool called SQ. And what this does is it tries to give somewhat more informative information about why your job might not have started yet and what might have gone wrong or how your job progressed for jobs that have already completed. And so what it looks like is if you run SQ, it'll show you things like sort of you're currently running pending or running jobs. And in this case, when I copied and pasted this, I had submitted a job, it was still pending, and this says, oh, this job hasn't run yet because it's scheduled to run after 21 higher priority jobs. And this also gives some information about jobs that have completed, and it says, oh, there was a job that only took 16 seconds to run, so maybe something went wrong with it, and you should check on it. That it seems a little bit odd that it finished so quickly. So that's a handy tool you can use to try and get a sense of sort of why things are happening the way they are with your jobs on the system. Okay, so let me turn it over to Clint.
Thanks, Chris. And so I'm going to talk a little bit about Open on Demand first, which I think has come up a couple times already. Yeah, so there's sort of an alternative way to access Savio that is sort of web browser based. And so it's a little different than what Christian talked about earlier. And that's called Open on Demand. And so you can use Open on Demand to view, download, and upload files on Savio, view the status of your current jobs on Savio, start a shell session, like terminal access, launch a Jupyter server, an RStudio server, or a VS Code server. This is also a way you can access a MATLAB interface as well. And you can also, I think it's currently under maintenance, but generally you'll be able to access Linux desktop on Savio as well. So you can do a really wide range of things on Open on Demand. And so first off, let's talk about logging into Open on Demand. It's sort of very similar to logging into SSH to some extent, with the one difference is that you don't have to type the second portion of the login, the @hpc.berkeley.edu. So I'm going to open this in a new tab, and you type in your username, and then you type in your PIN and then your authenticator, just like with the SSH login. And so that will load Open on Demand, and you can see I have modules across the top, and I'm logged in under my account. So first off, I wanted to talk about the file browser in Open on Demand. The file browser is right here. You click on Files and then on Home Directory. The file browser will always open in your home directory, just like if you log on to the SFTP server. And so you can see I have my files here. The easiest way to sort of jump to scratch, for example, would be to use this go to. So I can do go to, and then I can change home to scratch. And if I hit OK, that will take me to my scratch directory. And if I want to go back to my home directory, I can use this command again to jump around. You can also actually change the URL, but that will require the page to reload, and so it will take longer. So I'd recommend using the go to button. There's a download button if you want to download files. There's an upload button if you want to upload files. You can view files and edit files. Do note that if you're editing files, you're going to want to be sure to hit the save button when you're done. There's no autosave, and so if you're editing files in Open On Demand, be super careful about hitting the save button as an FYI. And there's also the show dot files. This might be relevant if you want to edit your bash RC file, for example. The show dot files checkbox up here is important and might be easy to miss. And so I did just want to say Open On Demand is a great, easy way to move and download and upload small files from Savio. But if you're going to do large file transfers, sort of Globus is going to be your best option. It will still take quite a while on Open On Demand. But if you're doing a small file, let's say you're uploading a Python script, Open On Demand would be a very easy way to do that. There's the feature that I mentioned that you can access your active jobs. So I'm going to click on Jobs and then Active Jobs. That will open up a new tab where I can see my job. So I have one job running for Open On Demand using Jupyter, which I'll talk about soon. And that sort of lets me see the status of the job. And sometimes it would also say like pending or something different if my job wasn't currently running. Then lastly, if you want to get access to a shell script, you can click on clusters in VRC shell access. One nice thing, I saw someone asked in the chat earlier, if you wanted to open up multiple terminal sessions, could you do that without entering your one-time password every time? And you can actually do that in Savio, on Open On Demand. I only had to type in my password once and I can open up multiple different shell sessions. And so just as an FYI, if you wanted to submit a job in Open On Demand, currently there isn't a easier tool for doing that. So what you would want to do is open the file browser, then upload or create/edit a job submission script. I may have forgotten to mention this, but if you look at the file browser, there is a new file button. So you could create a new text file and then edit it in the Open On Demand editor. And then you can open a shell session and you'd submit the job using SBatch like Chris discussed earlier. And so you can do all of the job submission parts using Open On Demand and not sort of using an SSH platform outside of your web browser. And so that is Open On Demand. So that's sort of an easy way to access the tools. And then next, I wanted to talk about doing a Jupyter session in Open On Demand. Some of the stuff I'll say here is sort of similar for setting up an R server or VS Code server or a MATLAB. I'm going to do a Jupyter example. So to do this, you're going to go to Open On Demand and click on Interactive Apps. You'll note there's several options here. In particular, for RStudio server and Jupyter server, there's two options. So there's compute on a shared node for exploration or debugging, and compute via Slurm using partitions. And so if you're going to do the compute on the shared node, this is going to give you access to very minimal computing resources. So I would suggest that you only use this if you're just doing some basic testing. What packages can I import, for example? If you're going to try running seriously intensive code, you're going to want to use the compute via Slurm and Savio partitions option. So as an example of what that would look like, you'd click on this option. You can name the job whatever you want. In this particular case, I'll just leave it as the default name. Then you select your partition. So for the other job I'm running, I selected Savio 3 HTC, for example. There's the account or project. For this, I'm going to use this ACSCS guest account, but you could also use a condo account or a faculty computing allowance. The QoS is one I particularly wanted to mention. So it defaults to debug. However, you're generally going to want to use Savio normal and not Savio debug. So please be advised of that particular point. Next, you can select a number of compute nodes. The options might vary slightly from partition to partition. Because this is Savio 3 HTC, I can select the number of cores per node. And so for example, I could do 4. 4 is going to be the number that I'm using in my example. And then you can select the wall clock time. So depending on how you want the maximum amount of time you want your session to run, you can set your wall clock time to that. But bear in mind, of course, that you'll be charged for the full time the session is running, even if you don't have the Jupyter session open. If you want to receive an email when the session starts, you can put your email down here, and then you would hit launch. And so once you hit launch, it will take you to a page with your interactive sessions. And so I'm going to open the My Interactive Sessions page. And this is this sort of thing here is sort of what an ended job looks like. Normally, when you launch a job, it will sort of give you a pending notice, and you'll have to wait a few seconds before your job will start. In this particular case, my job has already started, so I can just click connect to Jupyter, and that will open up my Jupyter session. So now that I have Jupyter open, I'm going to use this sample notebook I have created. And so there is a link if you're following along in the slides to where that notebook is on the GitHub if you want to follow along that way. But also the code that I'm going to run is here in the slides as well. So now that I have this notebook open, I'm going to talk a little bit about IPyParallel. There's multiple ways to do parallelization in Savio. IPyParallel is one particularly common tool. I'm going to do a sort of shared memory single node example. With a little bit of extra tooling, you can get IPyParallel to work on multiple nodes. But again, I'm just going to do a one node example to keep things simple. So first off, I'm going to import some packages and start a cluster. So I'm importing the OS package, the IPyParallel package. The reason I imported the OS package was to get the number of CPUs on the node. And so that's what this line right here is doing. It's getting me the number of CPUs on the node. And that way I can start up a cluster in the next line. So I use the cluster command. I set the number of engines. And so engines is sort of like the number of workers, basically. So generally, you want one worker for each CPU. It might depend slightly on your use case, but in this case, I want one worker for each CPU. So I set that option. And then I run this start and connect sync command. And so that will set up my remote cluster. So the RC is for remote cluster in this case. And as you may have seen, that started up 4 engines, and it sort of gave me this nice loading bar as well. So now I've created my cluster. How do I use it? How do I work with it? So the first and sort of basic way of using the remote cluster in IPyParallel is using a direct view. And so that remote cluster object, it sort of has different sort of engines within it, if that makes sense, is sort of how you can think of it. And so for the direct view, I'm going to want to access all my engines, and that's why it sort of looks like I'm indexing all of the objects from the remote cluster. Then, once I've created my direct view to all of the engines, then I can import packages on all of them. And so a direct view runs things sort of symmetrically across engines. So for example, if you have 10 tasks and you have 5 engines, it will give 2 tasks to each engine. Or if you ask it to run one command, it will run it on all of the engines. So it's very helpful for importing packages, for example. There's 2 ways to do that. There's this execute command, which will let you execute one line of code. And there is this sync imports command. And the sync imports command is probably the more typical way of importing packages. But I wanted to mention this execute command because sometimes it's helpful to be able to run one line of code, for example. And so next, how do you, the engines don't share the same data as your sort of main process. And so if you want the engine to have data, you need to share it with the engine. And so the way you do that is with the push command. And so, for example, I'm going to create an object called A on all of the engines with this value, and an object called B with this value. And that's what this push command will do. Let's say you want to send a different thing to each of your engines. You can do that by sort of indexing the individual engine and using the push command. So for example, here I'm telling each engine what its ID number is. So that's what that for loop does. The next step to working with IPyParallel is understanding what an asynchronous object is. And so asynchronous objects are sort of, well, they sort of look like this. And so what I did here was I ran on my direct view an apply command. So I asked each of the engines to run this command with this input. So this lambda function, which adds the ID plus X to the number 27. And then the result actually from that command looks like this. So it's not actually the numbers I want. To get the numbers from the asynchronous object, I also have to run the get command. But generally, you just sort of want your data. And so you don't need to use asynchronous objects. And there's a couple ways to do that. First, I can just run the apply sync command and it will return the object for me. I won't have to do the get command also. If I want to run a lot of those commands, I can run this blocking. So I can make all of the operations wait until the computation has completed. And then my dview command, this apply command, instead of returning an asynchronous object, will return the calculated out. And so that's what you can see here is I sort of set the operation to be blocking and said, don't give me the asynchronous object, just wait and give me the result. And that's what's happening now. The more in general, one of the very common ways of using IPyParallel is to run what's called a map. And so a map takes a bunch of inputs and runs a function on all of them. And I mentioned earlier that if you do this on a direct view, so if I had 8 tasks and I had four engines, which I currently do, then it would give each of the engines 2 tasks. And this might be potentially inefficient because you could imagine it's possible that the one engine will finish its 2 tasks while the one engine is still working on its first task. And so to sort of prevent this inefficiency from happening, you can use what's called a load balanced view. And what a load balanced view will do is it will sort of balance the load. And so if one engine finishes early, it will give that engine more stuff to work on. If one engine's tasks are taking longer, it will give that engine less to work on so that all of the engines are working with optimal efficiency. For ease, I'm going to enable blocking on my load balanced view. And so just as an example, I'm going to do sort of a Monte Carlo Python simulation, which just checks if 2 random numbers are in the unit circle, basically, and returns a 1 if they are and a 0 if they aren't. And so to do that, I'm going to need to generate some random numbers. So that's what I'm doing here. And then I want to execute my map command. So I take my LView and then I run my map with this function I defined above on my random numbers. And so you can see that the object that my random numbers are sort of like a list of pairs of numbers, a list of small lists, if you will. And so I'm going to run my map, and my map function will give a pair of 2 numbers to the function repeatedly. And so I'm going to run that. It should take about 7 seconds if it does the same as when I was testing. And then it will give me my result. And so you can see it took about 7 seconds. And so using a map is probably the most common way of doing parallel programming because it's very simple. You have one function, you have a set of inputs, and then you want to run the function given your different inputs. However, like I mentioned with the apply command, there are many different ways to do parallel processing. Just sort of as a side note for the people who are very into efficiency, parallel programming isn't always the most efficient. So you can see I can actually do that computation more efficiently just using a vectorized command. So that's just one sort of interesting point about this example. But in general, for sort of more complex tasks, parallel programming can really help you calculate things much faster. And so just to conclude, IPyParallel, you can set up a cluster in one line. It's an easy way to get going. Blocking is important. You don't want to get asynchronous objects. You generally want to wait for your result to be computed. Using a load balanced view will help you make the most of your resources. And I didn't demonstrate this, but IPyParallel can be used with multiple nodes if you're willing to accept a little bit more complexity. And so the last thing I wanted to mention is that there are other options for doing parallel programming. A really great one is called Dask. And so let's say you have a really large data set, perhaps it's a CSV, perhaps it's a Parquet file, and you want to load that onto Savio. You might find that if you have 500 gigabytes of data, you can't load this all into memory on a node that only has 50 gigabytes of RAM. And Dask will help you do this, basically. It will sort of take care of the memory management for you in a very nice way. It can also help with doing parallel computations as well. So it can also replace some of the functionality like maps that I just demonstrated with IPyParallel. And just to conclude, if you need additional help, you can check our status and announcement page. So if you're ever concerned that the cluster might be down, we have an email here for technical issues and questions about Savio. If you have broader questions about computing resources in general, maybe even cloud computing, there's a different email. And if you're interested in that secure research computing or research data management, there's our research data management email here. And for computing resources, which would also include Savio support, and for our research data management team, we have office hours twice a week for an hour and a half on Wednesday afternoon and an hour and a half on Thursday morning.